Welcome to Chapter 6, section in Earth and Science. Earth Science, this is the rock chapter. So to start off with, rocks are the solid part of the Earth. It could be a collection of minerals, could be a single element, but there are three main types. Igneous translates to from fire. These are the ones that cooled from molten magma. Sedimentary rocks are hardened, pressed, or cemented together sediments, which are fragments that are broken down. They're either chunks of other rocks that are already existing and have weathered away, or they could be organic matter. And finally, metamorphic. These are the changed form rocks. So for these, they were subjected to tremendous heat and pressure. They have altered an existing rock, but they're not brand new. They didn't melt and they haven't weathered away. They've just changed a rock that was already in place. All of these can go through the rock cycle. A bit of a dated idea, but the general theme here is any rock can go to any other location. So if I've got magma that cools, it could form an igneous rock. That igneous rock might melt again and then cool again to form another igneous rock. It might weather and turn into a sedimentary rock, or it might go through heat and pressure and become a metamorphic rock, which again could melt and start this whole process over again. Any one of these rocks could go any direction. So it's not so much a pattern. One rock leads to another, leads to another. It's more the idea that any of these processes could happen. They could weather, they could melt, they could get changed with heat or pressure, and ultimately result in a different rock. Every rock has a set of chemical and physical properties. These are usually determined by, almost always determined by how the rock's formed and the minerals that make it up. If we look at Bowen's reaction series, this is kind of putting them in order with reference to temperature and heat. So up here around 1400 degrees, you get olivine that can form. So everything's liquid up here, it's molten, it's cooling down, 1400 degrees, boom, olivine can come in. Drop down to, say, 1300 degrees, and then you're into pyroxene. Amphibole a little bit lower, and then on to biotite. And the inverse is also true. If it's starting to melt, you've got quartz down here at 800. Quartz will start to melt at 800. Then you're up to 900 for muscovite, and then it has to hit 1,000 before orthoclase is going to melt. So these are kind of rungs on a ladder is the way I describe them. Each and every one can change. So if we look at the chemical and physical stability of a rock, it's going to alter. These rocks can be formed deep under the earth under a lot of pressure and heat. As they cool, they get exposed to the surface. Well, if it was put under a lot of heat and that that heat is dropped, if it cools, the rock will actually contract, and that's one possible way that you can get all of these joints and fractures. The other option is it was under a lot of pressure down below. As it came up, the pressure released and the rock began to open up. It exposed these cracks or fractures just because it wasn't under as much pressure anymore. It wasn't held together. Now, those are both examples of physical stability. Chemical stability could relate back to the minerals that make up the rocks. Possibly you're dealing with rocks that dissolve when exposed to water and acid, like limestone or marble. And others are far less likely to weather chemically, like quartz or sand. So they really come down to how it's formed and the minerals that make it up. We're moving on to igneous rocks. So again, these are the ones formed from molten rock. We'll start off with partial melting. In this one, the idea is you start off with a cool rock, maybe 100 degrees, not hot enough to melt anything. It warms up a little bit. We start to get up to 400, 500, 600. Things might begin to melt just a little bit. When you hit that 800 to 900 mark, you're starting to get some material leaving. You're starting to get quartz and some of the others that'll melt away, and then finally you'll reach a point where it gets hot enough, everything melts. So partial melting is picking apart the parts that melt first. Each and every one of these pieces begins to melt at a different temperature. And as you increase the temperature, more and more of it melt. Fractional crystallizations go in the exact opposite way. Here you've got something that's 1400, 1200 degrees, something like that. It is cooling down, so olivines begins to form. And then you get down and you get into maybe amphiboles or some of the others. And then there are others that form and others that form. Each and every time these crystals form, they take elements, they take something out of the magma to make those crystals. So it could be minerals, could be elements, but since they're pulling it out of the magma, they're changing what's in the magma. End result is you've changed the chemical composition, you've changed the makeup of the magma every time these crystals get pulled out. Fractional crystallization and partial melting are both they're the same idea, they're just working in opposite directions. So if things have to get a lot cooler before one crystal will form, they don't have to get as hot for that same crystal to melt. It melts and forms roughly around the same temperature. If we look at cooling histories, intrusive rocks that are going to form down here inside the Earth's surface, inside the crust. Extrusive are up on top. That's going to impact the nature of the material. So for textures, we can have coarse-grained, like this granite up here. You see large crystals had a long time to cool. The longer it has to cool, the longer the crystals have to grow. You can form a larger structure. You can have intrusive, that is intrusive. The cooling history is slower and longer. You can also have extrusive, which tend to be much smaller crystals. So for these, we've got basalt is a good example here. Not a lot of time for the crystals to form. Everything cools rapidly. Porphyritic, my best examples down here. This is when it started cooling slowly and grew some large crystals at higher temperatures, and then it got pushed closer to the surface and the rest cooled quickly. That's why we have small crystal forms surrounding the larger crystals. You might also have glassy. This, again, has a very shiny appearance, looks a bit like glass. This is a good example of an extrusive rock that cools very quickly. The same is true for pumice over here, which is a vesicular texture. For this one, tiny gas bubbles were trapped in the structure and it cooled so quickly that they were left behind. Both of these are kind of flash cooled. Both of these got erupted out of a volcano and cooled very, very quickly. But one of them took on this really dark appearance. One of them trapped the gas bubbles in. For composition, felsic over here tends to be the lighter colors. They tend to have more silica and they tend to have lower concentrations of heavy metals like magnesium and iron. Mafic, going down to this side of things, tend to be much darker. They tend to have less silica and more metals. So your famous types, mafic, you're looking at basalt, gabbro. For felsic, you're over here, you're dealing with any number of things, but granite especially, but also pumice, obsidian, one we talked about before. You can also have an intermediate composition. This is the mix between the two. So there's a little bit of felsic and a little bit of mafic characteristics, and they're kind of in between. That's why they call it intermediate. The different ways igneous rocks cool they're called intrusions. And this is, again, not talking about the chemistry, but here talking about the physical way that it's put together. You can start off with a batholith. This is a massive structure, at least 100 kilometers squared at the surface. Translates to deep rock. These are mountain builders. These are the cores of some mountains. This is a huge quantity of magma. You can also have stocks, which are the same general idea. They're just not quite as large, less than 100 kilometers squared. Laccoliths is when you start getting magma that sort of pools and piles itself up. It actually translates to lake of rock. But what you see here is you see how all of these layers start to get deformed. They start to bump up. It's actually pushing its way up and forming a dome. It's not the same idea here. So you're not just kind of melting part of it. You're actually enlarging the area, creating a dome. You can have stocks, which we already mentioned. You can have sills, which is when magma kind of runs parallel. It doesn't really change the surface. It just kind of has a little bit of an offshoot here, and dikes, which are the ones that cut vertically. So they'll move through the different rock layers, melt across, and cool in place. But again, these are vertical, these are horizontal, running with the rock layers. For a volcano, we're all familiar with the general structure here. Magma rises, it's going to erupt out of the volcano if it erupts. If it doesn't erupt, it'll form a structure that is called a volcanic neck. Here, magma rose up in the volcano and did not erupt. It stopped, it cooled. End result was it hardened into this mass of cooled magma, this volcanic igneous rock, and it stopped. The rest of the volcano got weathered away and it was left behind. This is called a volcanic neck. Over here, we've got a lava flow. If this was on a large scale, we could be looking at a lava plateau, which is when it covers a very large area. This is an example of an extrusion. We looked at intrusions before. And down here, this is tuff. This is the large deposit of ash that is built up after a volcanic eruption. Getting into the sedimentary rocks, start with sediments are fragments of rocks, minerals, or other organic material. They take on the properties of what they're made of. So if you got rocks, they're made of rocks. It's going to have the same general idea, same properties. And ultimately, that's going to affect the properties of the sedimentary rock that it forms. If we look at how they're put together, you can have a process. So you start getting rock fragments that are all generally put in the same area. Over time, pressure forces down on them. You see where all these air spaces were here before, they start getting squeezed away and they're all pressed in together a little bit tighter. Over time, groundwater or rainwater, as the case may be, will actually start to deposit bits of minerals. This will cement the rocks together and start to fill up these void spaces, resulting in a sedimentary rock. The last option is a chemical precipitation, usually involved with evaporating water or changing chemistry. Here, the water evaporates away, it leaves behind layers of salt. We see this a lot when seas get trapped inland and you wind up with thick layers of salt left behind. For composition, if we get into the different ways they're put together, you can have some that are made of organic sedimentary rocks. They can be formed by the remains of living things, could be coal, could be limestone, good examples here. It could be clastic sedimentary rocks, little chunks of rocks that are put together that all get packed in around each other. The chemical sedimentary rocks we mentioned on the last slide, those were the ones where the salt or the other chemistry changed and it got left behind. The fragments are used a lot to classify sedimentary rocks. So conglomerate's a good example here. If you look at the pieces here, they're generally rounded. They have a round structure. There's a few exceptions, but most of them, they're larger than 2 millimeters in diameter, and they're rounded. They don't come to sharp points. Breccia, on the other hand, is very different. These are almost all angular. These are sharp angles, and that's one way to classify them. You could also get into down here, we can see that you can have sand-sized particles that are all put together. These are more of the sandstones. There's more pore space in these, tend to allow more water to get through, or mudstones, which has very little pore space. Not much water's getting through this. But shale is an example of a mudstone that gets compacted together. Tends to split easily as well. Now, transport is important for sedimentary rocks in the class that make them up. The further they go, the rounder they get, and the smaller they get. If they're getting bumped along the stream, every time they hit on a sharp corner, a little piece breaks off, and then another little piece breaks off. Over time, this is going to round the structures. So we can see here, these tend to be well-rounded. Over here, more angular, more sharp corners and edges. And it progresses toward more rounded. It also gets more sorted. So the further it goes, the smaller the pieces get, the better sorted they are. If it didn't travel very far, it would be poorly sorted. You could have large chunks in mixed around with all the small pieces, and they could also be very angular. For depositional environment, there are a few options here. This is anywhere that sediments are collecting, so it could be in lakes and rivers, along beaches or deltas, or especially and eventually they'll get out here into the oceans. They don't pile up on tops of mountains or on hilltops necessarily. These tend to be in the places where it's going down. Gravity is working on these. And we can also see stratification. Stratification is just the layering of the different sediments put into different bands. You see all these lines here, these are all layers, and each and every one of these is a bed. Beds are simply the stratified layers, the ones that have a unique signature. Now, some of these are massive. Some of them are made of the same stuff that's piled up really deep. Some of these are crossbed, so here we see the structures, generally lines built up here or here. A good example here, this is called crossbedding, usually forms long dunes. So if you can imagine the dune that used to have the general shape here, had layers built up. Well, that they got preserved. You can see grading in these. So large chunks down at the bottom, up to smaller at the top. You can also see inverse grading. So this is when it gets reversed, usually during a mud flow. There are mud cracks, which occur when you had a loss of water, the clay dried out. Same things can be seen at the edge of ponds today. Ripple marks, these are the ones that you see if you go to the beach, just in the shallows. The water passing across the top or the wind can actually lead to the development of these small ripple marks and structures that get preserved through time. Fossils are also commonly occurring. Simply put, remains of plants or animals. This could be traces as well, and concretions over here. These are chunks of rocks that don't really belong. These are the ones that are made up of stuff that's not like the rest of it. All right, to quickly get through metamorphic rocks here. These are the ones that get changed with heat and pressure. There are two main kinds here. Contact metamorphism, as we see here. This is going to be hot magma. It's going to alter the rocks right around it a lot, alter the rocks outside of them a little, and then very little bit as you get further away. Or regional. This is when you have a couple plates sliding into each other, a great deal of magma gets thrown around, and large areas are exposed to pressure, ultimately leading to metamorphic rocks on a large scale. There is some contact metamorphism associated with this, but it doesn't tend to be the primary cause of the change. If we look into foliated and unfoliated rocks, foliated are the ones with lines. The heat and pressure has realigned the minerals, the crystals, and ultimately results in different layers and bands that are formed here. Non-foliated, all the crystals are mixed. They're not set up in defined structures. They're a little bit mixed around everywhere. And they have different reasons. Non-foliated tend to be associated with either all the same material, so even if it does get mixed around, it can't line up because it's all the same, or the original rock had square round grains, so no real long sides to orient, no way to put them together in bands. Some examples here might be quartzite, made out of sand or marble, made from limestone. So ultimately, there is the gradation you can see in metamorphic rocks. So maybe a mudstone would go to a slate, and then a little bit more heat and pressure, it gets to a schist, and then eventually to a gneiss. But ultimately, metamorphic rocks are the change of heat and pressure. All right, hope this helps. Let me know if you have questions.